Hello, my name is Laura Crosilla and I'm a researcher at the University of Oslo. This is a video on infinity in mathematics, and infinity in mathematics is a topic of my research grant sponsored by the Horizon 2020 program of the European Union. This is the third of a series of videos on philosophical aspects of infinity in mathematics. In our second video, we introduced Aristotle's distinction between potential and actual infinity, and we also looked at Cantorian's higher infinity. In this video, we look at Russell's paradox and, among other things, the notion of circularity. To introduce Russell's paradox, it's good to look at what sometimes goes under the name of Barber's paradox. One might call it Barber's puzzle. This says that there is a barber who shaves all and only those who do not shave themselves. So now suppose we ask a question: does this barber shave himself? And we then have to reason like this, that suppose a barber shaves himself, then the barber does not shave himself. On the contrary, suppose that the barber does not shave himself, then the barber does shave himself. So the conclusion is that the barber shaves himself if and only if he does not shave himself. But so we reach this kind of puzzling conclusion. A question I would like to ask you is, do you think this is a paradox, or is it something else? Okay, let's remind ourselves of what a paradox is. At least the way we introduced the paradox in the previous video. A paradox, we said, is a statement, or perhaps a series of statements, which, together with apparently true premises and by seemingly uncontroversial reasoning, forces us to reach false or absurd conclusions. Now, given this notion of paradox, it's clear that we did get to some absurd conclusion, but if essentially we conclude that if there is a barber of that kind, then he does shave himself, if and only if he does not shave himself. However, it's quite clear that the barber is not a paradox. In fact, one might claim that it is simply a proof that there is no barber of this kind. So it simply shows that a barber who shaves all and only those who do not shave themselves cannot exist. So the way we can use this statement is as follows. We say, okay, we suppose there is a barber who shaves himself if and only if who shaves all those and only those who do not shave themselves. Then we reach a contradiction, reach an absurd conclusion. Therefore, the assumption we made that there could be a barber of this kind makes no sense, and therefore we have reached the conclusion that there is no barber of this kind. So this is what sometimes is called a proof of a negation by absurdum. We show that if we assume something, we reach a contradiction, then that something simply cannot happen, cannot be the case. But let's then move on to a real paradox. So we want to go to introduce Russell's paradox. In order to do that, it's good to remind ourselves of a concept we hinted at already in the previous video, that of naive sets. So, according to a naive concept of set, a set is a collection of some things, of some objects or things. So, for example, a collection of some people can be considered to form a set. The collection of the eggs in my refrigerator form a set. A certain collection of numbers, for example, numbers 1, 2, 3, 4, 5, form a set, and so on. One could also consider words, thoughts, and so on. We want to leave this notion of set very, very generic and general. We just think about some things put together. So you consider not just the things, as we said last time, but also the fact that these are together. You consider these objects, for example, the eggs in my refrigerator, not just as individual eggs, but as those eggs together forming a whole. We call things that together form a set. For example, the people, or in a certain set of people, some eggs in my refrigerator, and so on. We call these things the elements of a appropriate set, and we say that they belong to that set. So here's what I want to stress is the terminology. We talk about sets, we talk about elements of a set, and we say that the elements belong to a set. Now, given a subset C, one might ask this question: does C belong to C? Does C belong to itself? And one will clearly see that sometimes yes, sometimes not. In some cases, a set C could belong to itself, will belong to itself. In some other cases, a set does not belong to itself. So let's see two examples. So take the first example. Take a set of all the words they appear on this slide, on this page. And let's call it A. Now you ask the question, does A belong to A? So when you ask the question, does A belong to A, you want to see if A is one of the elements of a set A. So it means that you want to see if A is a word on this page. But the collection of all words on this page is clearly not a word. It is not something like a word which can appear on this page. So therefore, it does not belong to A. Okay, let's see its second example. Example 2. Take now a set of all those things that are not words on this page. So everything which is not a word on this page. Let's call this collection of all these things B. If you ask, does B belong to B? Well, in this case, we clearly have to say yes, of course. So B is a set of objects of many different kind. For example, the eggs in my refrigerator will be in B. So B, however, is not a word, in particular not a word on this page. So therefore, it does belong to B. Okay, so let's see now Russell's paradox. Russell's paradox arises if we consider the following sentence. Let R be the set of all and only those sets that do not belong to themselves. So you take all of those things which have this property of not belonging to themselves. All the sets which have a property of not belonging to themselves. And then you ask this tricky question, a question one should never ask, which is, does R belong to R? And the reasoning now goes in a similar way as we already saw a few times in this series of videos. So suppose that R belongs to R. Then R is an element of those things, with those sets which do not belong to themselves. So therefore R does not belong to R. Now suppose that R does not belong to R. Then if R does not belong to R, then R satisfies the property of those things which are in R. So R does belong to R. So we then have reached this contradictory conclusion that R belongs to R if and only if R does not belong to R, which is clearly a contradiction. So in this case, we clearly have a paradox. So we are not like in the case of the Barber's puzzle, providing a proof of that something does not exist. We have postulated the existence of this R in this way, and we have reached a contradiction. So last time we saw important changes which took place within mathematics at the beginning of from the beginning of the 19th century. And I reminded you of this beautiful way of phrasing these changes by Howard Stein, who claimed that mathematics underwent a transformation so profound that it is not too much to call it a second birth of a subject. It is its first birth having occurred among the ancient Greeks. So we have this rebirth, a new birth of mathematics. So one of the most significant changes which relate to this, one of the most significant changes which took place at that time relates to the concept of infinity, and really was prompted by Cantorian set theory, the ideas by Cantor. So the idea is that a paradox like the one discovered by Russell at the beginning of the 20th century put extreme strain on the reflections which were taking place around the time on the new kind of mathematics. So mathematics had undergone deep changes. Mathematics also, the foundations of mathematics set theory also underwent gave rise to some problematic situation, gave rise to paradoxes. So this brought many to think that it was urgent to come to some sort of clarification of what was going on in mathematics. And in particular, so one had to clarify whether the new methodology was correct, was giving rise to correct forms of mathematics. And one also was wondering whether the new concept of infinity, which had been put forward, especially through Cantor's set theory, was perhaps a source of some of the trouble. So whether one could use safely the actual infinite in mathematics. So one could say the Russell's paradox showed that the naive concept of set was giving rise to puzzles, and that was indeed problematic, and that a more careful approach was needed in order to develop set theory. In fact, it's important to note that Cantor himself had already realized that one had to be particularly careful when formulating set theory, because one easily came to paradoxes analogous to Russell's paradox. Okay, so there's no time to go into the details of how Cantor replied to that, but just to say he was already quite aware of some of the difficulties one might encounter if one does not develop a more sophisticated notion of a set. The point which is important for us today is that the combination of the deep methodological changes in mathematics with paradoxes like Russell's made a reflection on the foundations of mathematics particularly urgent. And this gave rise to wonderful philosophical reflection, so a sort of golden era for the philosophy of mathematics. One of the main actors in this respect is the German mathematician David Hilbert, who was one of the most prominent and influential mathematicians of his time. He contributed in an incredible number of new ideas in a large number of areas in mathematics. He had this sort of wonderful ability to work in very different areas in mathematics. So, as we already hinted at in the previous video, Hilbert did embrace the new methods. In particular, he embraced Cantor's set theory. However, he took seriously the challenges that arise from paradoxes like Russell's and the challenge of clarifying the new methodology. In particular, clarifying why we could trust these new methods, and in particular, the new way of looking at infinity. In fact, Hilbert himself gave fundamental proofs which use the new methodology, and sometimes with results which were quite surprising for his contemporary mathematicians. So it's well known that the mathematician Paul Gordon made following remark when he saw for the first time Hilbert's proof of what goes under the name of Hilbert's basis theorem. This is a very elegant, quick proof that Hilbert devised, and which showed really the power and the potential of a new methodology. So Paul Gordon is said to have said that this is not mathematics, this is theology. I will try to clarify later on in which sense one might understand this remark by Gordon, that this is not, Hilbert's proof was not mathematics, rather theology. So we saw that Hilbert, on one side, thought that we should make the most of the mathematical progress and use the new ideas. On the other side, he thought that this should not be done without also providing a proper justification for the new methodology. So it's important for this, in this respect, to to review this, to read together this little extract from the article on the infinite from 1926, where Hilbert writes that from time immemorial, the infinite has steered men's emotions more than any other question. Hardly any other idea has stimulated the mind so fruitfully, yet no other concept needs clarification more than it does. So on one side you have this positive view of infinity as stimulating the mind. We saw something very similar in Hermann Weyl, a quotation from Hermann Weyl in a previous video, where Hermann Weyl also thought that this difficulties that we face when trying to do mathematics of the infinite, when we're reflecting about the infinite, are fruitful. This tension between the finite and the infinite, already the ancient Greek found and noticed, can be a good source of progress and new knowledge. And this seems to be also what Hilbert thinks. However, Hilbert also, as much as Weyl indeed, recognizes that there is a need for clarification of so the infinite needs urgent clarification. And when Hilbert talks about the infinite required clarification, it is especially the use that we notice, especially in set theory, of the concept of actual infinity. So the worry is really the fact that the mathematics has changed so much, and in particular, infinite is now treated freely and even by as if, say, the actual infinite was really part of our mathematics. So Hilbert called this new part of mathematics Cantor's set theory, in particular his theory of transfinite numbers, the cardinal and infinitary cardinal and ordinals that we already hinted at in the previous video. He covered the most admirable flower of the mathematical intellect. And as we already saw, he also claimed that no one shall expel us from a paradise which Cantor has created for us. So we should try to keep this wonderful mathematics, but we need to make sense of this new role for actual infinity in mathematics, especially its role within set theory. And he thought, indeed, he could offer a good, a once-for-all justification of these uses of the actual infinity in mathematics. So how did he thought he could do that? Well, he offered what is known as Hilbert's program. This is it would require more space. Just very, very briefly hinting at the main points, one could say that Hilbert's program wanted to use the axiomatic method, so using essentially codifying a part of mathematics, say for example algebra or analysis, in terms of some axioms, or geometry, as Hilbert did, in terms of some axioms, which clarify in a very precise sense what this area of mathematics is about. And then the idea was one would combine the axiomatic method with something that Hilbert himself devised from scratch, a new area, which Hilbert and his collaborators, in particular Paul Bernays and others, and this was called proof theory. So the idea is to give rise to a new field, proof theory, which together with the axiomatic method was meant to offer a definitive finitary justification of the use of the actual infinity in mathematics. In particular, was something which would allow us to justify Cantor's paradise in a sense. So I cannot go in more detail into this. If you want to see a bit more, you can have a look at the Stanford Encyclopedia of Philosophy, the article on Hilbert's program, and you can see how Hilbert's program was proposed. So what we will see in the next, in the last video of this series, is a view which is very different in many respects from Hilbert. So a view of Cantor's infinity and Cantor's paradise that shares with Hilbert the thought that there is a problematic aspect to the use of the actual infinite, but also tries to find a different way out. So as we will see, the way out is a bit more restricted than what Hilbert was trying to do. That's what we'll see next time. So let's conclude this video today with a couple of thoughts about what the paradox taught us. So indeed, Henri Poincaré is one of the main authors I will discuss in the next video. And we already saw Bertrand Russell. So around 1905, there was an interesting exchange between Poincaré and Russell, on which was prompted by Russell's paradox and touches many issues and many points, in particular also this question of how do we justify the new forms of mathematics. And thought, so while Poincaré and Russell disagreed in many respects, in particular their philosophical views are extremely different, Russell and Poincaré agreed on a very important point. So they both thought that the sort of the paradoxes like Russell's were caused by a form of vicious circularity. So they noticed a form of circularity in definitions like that of R, which is a set of all those sets that do not belong to themselves. So the idea is that we define R by reference to a collection of all sets, and then we are trying to argue that R is one of those. So we get a form of circularity. And the thought is that this kind of circularity is bad, it is vicious. So the thought is we define R in terms of a class to which R would seem to belong. We define R, therefore, in terms of itself, giving rise to a form of vicious circularity. Indeed, this idea of vicious circularity had been noticed by Richard and then taken up by Poincaré and Russell in this exchange. So Poincaré and Russell thought that this circularity in definition was not only common characteristics of many paradoxes, but something which should be thoroughly avoided. So they thought that good mathematical definitions should be non-circular or predicative. So the idea is the following. We have deep radical changes within the mathematics of the 19th century. Some of these changes end up producing unwanted results, like Russell's paradox. So some people who thought about, some mathematicians who thought about this, came up with the conclusion that there was something wrong with the way we were introducing our notions. So one, in the case of at least Poincaré and Russell, one should have given better definitions of mathematical objects. So one should have particularly avoided this sort of circularity. And one should have done defined notions, what one would say, from step by step, from something simple to something more complicated, going from the bottom up. And the term which is usually used to characterize this non-vicious circular definition is predicative. Is a term which was introduced in this exchange between Poincaré and Russell. We'll see a little bit more about predicativity in the next video. I would like to conclude this video with the following thoughts. So in this video we have seen Russell's paradox, and we hinted at its troubling consequences for Cantorian set theory. We saw Hilbert's approach to these difficulties through his Hilbert's program. And then we saw the circularity that some authors like Poincaré and Russell thought was a key element of paradoxes such as Russell's. So next time we will look at what I like to call critical views of infinity, which go in a very different move from a very different perspective compared with Hilbert's on say the what we should be able to justify. So they tend to come to the conclusion that one should avoid certain kind of definitions, and then in a sense also accept a restriction of the kind of mathematics which is justified. Anyway, we'll see this in the next video for next time.